Good morning, good afternoon, or good evening, everybody, wherever you might be. It is my great pleasure to introduce Adam MAGEE, who will tell us about really fresh stuff, recent progress in twisted real structures for spectral triples. But before I hand over the Zoom, the screen, the internet to him, let me announce that in a week, our speaker will be Alan Cohn, who will speak about Riemann zeta functions and spectral triples. So if you want, in a week, we also have a spectral triple theme. But for the time being, it's Adam MAGEE, and we twist and shove. Sorry, we twist real structures. Sorry. It's all yours. Take it away.
Thank you very much for the introduction, Piotr. And thank you to the organizers for inviting me. As mentioned, this talk is on recent progress in twisted real structures for spectral triples. Since I have the luxury of 1.5 hours, I get to cover really more or less everything that I have. So the structure of the talk will be as follows. I'll start off with origins of real spectral triples and real structures. Then move into motivations for weakening the definition of a real structure, twisting the definition of a real structure, if you will. Motivations coming from conformal transformations. Then I'll talk about some work on Hodges spectral triples applications with Francesco D'Andrea and Ludwig Dombrowski, who are, I believe, in the audience. Then section 4 on gauge transformations, which is more work with Ludwig Dombrowski. Then I'll talk about twisted real structures for twisted spectral triples, just to get all of the twists involved. And then lastly, multi-twisted real structures as well. So without any further ado, I think if you want to talk about spectral triples, at some point you have to get Clifford algebras out of the way. So we'll start there. For a complex Clifford algebra, you always have a Z2 grading. And if you compose this Z2 grading with complex conjugation, you get what's called charge conjugation, which I'm denoting here by kappa. Now, suppose you have an irrep of your Clifford algebra on a Hilbert space. You can define on that Hilbert space an anti-unitary operator, which I'll call capital C. This can implement the charge conjugation as an antilinear isomorphism, like so. Why do you want to do this? Well, the complex Clifford algebra combined with the charge conjugation is basically a star algebra with the star structure coming from the charge conjugation. So the combination of your irrep little c and your anti-unitary operator big C gives you a star representation. And these star representations can be classified. How? Well, first, you note in very basic terms that your charge conjugation, the action of the charge conjugation on the Clifford algebra, is more or less entirely determined by the complexification of Rn, let's just say for the n-dimensional case. And this can be decomposed into a real subspace and an imaginary subspace, dimensions p and q respectively. And so the star representations of our star algebra here, the complex Clifford algebra with charge conjugation, are just given by the ordinary representations of a real Clifford algebra of signature PQ, where these PQ are the same as the PQ coming over here. Why is this useful? Well, the theory of real Clifford algebras is in some sense more rich than the complex case, because they exhibit these two symmetries. The first one is not as important, this 1-1 periodicity, as it's so called. But what's more useful is this 8-fold periodicity on the bottom. And from the perspective of representation theory, the presence of these full real matrix algebras here, which we're tensoring by, don't factor in at all. Because from the perspective of Morita equivalence, they're basically invisible. Because your C-star algebra tensored by some full real matrix algebra is going to be Morita equivalent to your original C-star algebra. So the fact that we have an 8-fold symmetry here the reason that it's richer is because in the complex case, if you only look at regular representations, you only have a twofold symmetry. So we have this quadrupling of interesting cases. So now we're going to lift this to manifolds and define a Clifford bundle as just the algebra bundle generated by the cotangent bundle over our Riemannian manifold, taking as the quadratic form of the Clifford algebra, just the metric basically, lifted to sections. Then Clifford module over our manifold is a finitely generated projective bimodule S, fancy S, script S here, which is a left module for sections of the Clifford bundle and a right module for continuous functions. And I'll say here that for almost all of this talk, when I'm talking about Riemannian manifolds, I mean compact. So for a complex vector bundle S, regular S, the Clifford module will just be sections of this complex vector bundle. And I know I'm overusing the letter S here, but the choice here is basically to stand for spinors. This is our complex vector bundle is going to be the spinor bundle. So the case that we're most interested in is when the Clifford module is irreducible. And that happens precisely when our fancy S is Morita equivalence bimodule. That is to say, it implements the Morita equivalence between the sections of the Clifford bundle and complex functions. And when that's the case, if the Riemannian manifold is also equipped with an orientation, the combination of the orientation and the Clifford module gives a spin C structure. And so the manifold will be spin C. In particular, we're interested in spin C manifolds because then we can for sure define Dirac operators. So furthermore, it turns out that the second Stiefel-Whitney class is zero exactly when there exists an antiunitary operator on our fancy S called C, not coincidentally, which is compatible with the left and right actions. On the right, just coming from functions, it's just a complex conjugation, but on the left, you can see here, it's implementing the charge conjugation that we had before, just now lifted to the bundle structure. And provided that this antiunitary exists, again, combined with our spin C structure, now we have a spin structure and M is spin. So this antiunitary operator is effectively discriminating between spin and spin C structures.
So can you remind me what this chi stands for?
Yeah, chi, this is so for the Clifford algebra, this is just the grading.
Mm-hmm.
And for the Clifford bundle, this is just the same thing, but now globalized, exactly, yes. Okay, so shifting gears a little bit, suppose now that we take some pre-C star algebra represented on a Hilbert space, so A represented on H. On that Hilbert space, for some unbounded self-adjoint operator with compact resolvent, which has bounded commutators with the algebra, what I'll call D, a generalized Dirac operator, we can always obtain a pre-Fredholm module via the bounded transform. This F will be a Fredholm operator. Why do we want to do this? Any pre-Fredholm module gives us a class in K-homology, and all such classes are obtained in this way. And so whether we have a pre-Fredholm module or a spectral triple, where we take D instead, we get the same stuff from a topological perspective. So our spectral triple is motivated as an unbounded K-cycle. It's easier to work with Dirac operators than Fredholm operators, so better to take spectral triples. Now, provided the algebra has an involution, which is compatible, we can incorporate an action of the real Clifford algebra.
Excuse me?
Yes.
If you say that all classes are obtained in this way, you mean classes on this pre-C star algebra or the completion, C star completion?
Good question.
Probably you mean the sister completion, yes?
Yeah, I believe so, yeah.
Okay. Okay, thank you.
No problem. Yes, so we can incorporate in certain occasions the action of the real Clifford algebra. And the idea behind this is more or less taking inspiration from what we've already seen. You want to use the fact that from the perspective of representations, the real Clifford algebras are just complex Clifford algebras with charge conjugation. And we want the charge conjugation to be implemented by some antiunitary. The issue with this procedure is that, in general, a representation of a real Clifford algebra on a Hilbert space will not be irreducible. But we can reduce the chaos cycle in such a way that you can get an irrep, but in doing so, you go from something with signature PQ to something with signature J0 or 0J, where J is just P minus Q mod 8 or Q minus P on some dense subspace. And what you get in going from the chaos cycle to the reduced chaos cycle is all of the operators have the same properties as before, but the price that you pay for the reduction is the introduction of these terms, so these signs. Previously, for the full chaos cycle, these are all pluses, but now we have choice of 3 signs. So 3 signs gives us 8 total combinations, and in fact, those 8 combinations coincide precisely with the 8 possibilities that we can take for J. So it's all fitting together. And this is incidentally what I meant if you read my abstract about refinement in K-homology, because if you don't incorporate this action, or if you just work in spectral triples and not real spectral triples where we're headed, you only have 2 classes, even and odd, basically. So now here we have, again, a quadrupling. So, like I said, we want to head towards real spectral triples. There are 2 main sources of inspiration. One is the definition of the reduced KRJ cycle, which we just saw. And the other one comes from the modular conjugation of Tomita-Takasaki theory. So the definition of a real spectral triple, which I'll give here, as you can see, is exactly the same as that for a reduced KRJ cycle, where here the table of signs is given explicitly. But in addition, and this is where the inspiration from Tomita-Takasaki comes from, we want our antilinear isometry, our antiunitary operator, which I now call J, to implement what's sometimes called the reality condition or the 0th order condition. Basically, it takes the algebra to its commutant. And using this, you can further define what's called the 1st order condition, where these commutators of the Dirac operator with the algebra, which from now on I'll just call 1 forms, because that's effectively what they are in this framework, where these commute with elements of JAJ. And it's called the 1st order condition because this is just, in the commutative case, equivalent to an algebraic way of formulating that your Dirac operator is a 1st order differential operator. So for an example of a non-commutative real spectral triple, the classic archetype is the non-commutative torus. This is, in as few words as possible, the 2 torus case. So you have this extremely well-known C-star algebra for the non-commutative torus, along with the Hilbert space, which basically comes from the same stuff. The Dirac operator is just given by 2 very natural derivations, which have this action on the C2 part coming from Pauli matrices. The real structure comes again on this C2 part via the Tomita-Takasaki operator, and gamma is just the natural Z2 grading on the doubling. Oh, and of course, in the commutative case, as you can imagine from the construction, spin manifolds are the other typical example, the canonical spectral triple, which I'm sure everyone's seen a million times. So we have lots of examples of spectral triples from all areas of mathematics and physics, but often they don't exhibit a real structure. And indeed, in some cases, they don't even admit a real structure. So as well motivated as our definition of a real spectral triple is, a question you can ask is whether it's too restrictive, or flipping that on its head, is there some way to weaken the definition, to broaden it, to generalize it, so that we can extend the machinery of real spectral triples to more examples? So that brings us nicely to section 2.
And could you tell us why this reality is so important and needed?
So from my perspective, at least, someone who comes very much from a physics background, it's really important to have the real structure if you want to have gauge theories. That's, for me, the main thing. It's really a crucial ingredient. Another way that you can look at it is that if you want to take the perspective of the real structure being a kind of non-commutative spin condition, then weakening it could kind of extend some of the properties in some non-commutative way of spin manifolds to a wider class of manifolds, some kind of pseudo-spin, I guess. Apart from that, I think also as well, okay, the fact that it's also frequently very easy to find modular conjugations, because of course you're working in most of the time on bounded operators. And so by taking double commutants, you can get Tomita-Takasaki operators, but that doesn't mean that you can really use them for much. So also being able to bring more elements of Tomita-Takasaki theory into play. It's basically just having more tools is always a good thing, I think. So for conformal transformations, let's return back to the standard commutative case. We have a spin manifold. A conformal transformation of the metric is just a rescaling of the metric by the square of what I'll call the Weil factor, which is just some real function. The transformation of the Dirac operator, which corresponds to this rescaling of the metric, is basically just given by sandwiching the Dirac operator by the inverse square root of the Weil factor. But in the case that the algebra is non-commutative, trying this same trick of taking a positive element of the algebra, sandwiching the Dirac operator by it, doesn't even give you a spectral triple back, but instead you get a twisted spectral triple. What is a twisted spectral triple? Well, a twisted spectral triple is basically the same thing as a spectral triple, but instead of requiring that you have bounded commutators of the Dirac operator with the algebra, now you require that you have bounded twisted commutators, where usually the twist you take as coming from the automorphisms of the algebra. It's a concept which is, in the context of non-commutative geometry, not new, but not old. But this definition for a real twisted spectral triple is a little bit more recent. It comes from a paper by Lundin Martinelli in 2016. And they extend the idea of a real spectral triple to the twisted setting in a very natural way. Basically, the only real difference from, if you merge the definitions for a twisted spectral triple and a real spectral triple, this is more or less what you'll get, with the only things of note being in the first order condition. The inner commutator, of course, will be bounded. This is just one form, so twisted one forms. But also the outer commutator will be twisted, sorry. And the twist on the outer commutator will just come from the original twist up to some compatibility with the real structure. If you include a star here, then this row will usually be inverse, because actually row is not usually a star automorphism. But that's not super important here. So, okay, let's say that we have a real spectral triple. We conformally transform it like we saw before. What we end up with is a real twisted spectral triple, where again, our Dirac operator is just D sandwiched by K, and the twist automorphism is coming from the Weil factor, just conjugation by the Weil factor. And okay, this is a twisted spectral triple. It's all good in that sense. And okay, from the perspective of K-homology, things are all right, provided that the Dirac operator is Lipschitz regular. But now you can already see that things are getting a little bit complicated because we've taken a step away from the very well-known, deep, expansive literature on spectral triples. And not to say that there's not a lot of scope in twisted spectral triples. I actually think it's a very interesting area. But it's just that a lot of the resources aren't there yet. There are still a lot of theorems waiting to be proved. So it's not
just a naive
yeah.
question, if I may. When you have the usual spectral triple, of course, you can do such a thing as taking the signature of a Dirac operator and get a Fredholm module, right?
Yeah.
So how about here? When I have a twisted spectral triple and I proceed in some similar fashion, will I get the usual K-homology class or something more twisted?
Truth be told, I'm not entirely sure. I don't know a lot about the details of Dirac operator theory in the context of twisted spectral triples. I think the answer is yes, if I remember right, under certain conditions.
Yeah, I think you get the same class, K homology class.
Yeah, but
yes,
also
the commutator is an ordinary commutator. I don't know whether I am correct, but you don't have to twist if you take the sign of the Dirac. But I'm not sure. Absolutely, I'm not sure. But
well, you
it's
take
correct.
Sign, but you take bounded
correct.
transform. You take bounded transform. Okay,
it's correct. If you take bounded transform, it's untwisted.
Okay, so I get the usual K-homology class, right?
Yes.
Okay, thanks.
Yes.
Provided it's Lipschitz regular.
Provided that this is Lipschitz regular, yeah.
Yes.
Yes.
Okay. Okay, yes, here have a, of course, yes. Good.
So point being, I guess motivation from that discussion, is there a way to sidestep such questions altogether? And the answer, it turns out, is yes. So this was shown in a paper by Brzezinski, Ciccoli, Dombrowski, and Sitash in 2016. The point is that if instead of sandwiching the Dirac operator by something coming from the algebra, from A, capital A, you instead sandwich it by something coming from JAJ, what you can do is retain the spectral triple structure. You don't have to twist the commutators anymore, but you have to pay some price, and the price you pay is that you get this extra operator nu, defined here, which factors into the commutation of J and D, the transform D. And also the first order condition is not satisfied anymore, but instead nu also appears here in this outer commutator. But still, we have a genuine spectral triple. And in the commutative case, you recover exactly all the normal stuff. So you can use this as a template to define a spectral triple with twisted real structure, where we have some twist operator nu, which we'll generally take to be bounded. It gives an automorphism of the algebra, like so, by conjugation. And we have some antilinear isometry J. And then again, we have nu factoring into the commutation relation of J and D. There's this twist on the outer commutator of the first order condition. So I might call this at some point a semi-twisted first order condition, just to contrast it with the twisted first order condition of the real twisted case. And also optionally, you have this regularity condition. And if there's a grading present, also some compatibility conditions with the grading, but it's not so critical. So everything's good, right? Well, not quite. In fact, there's still a lot about conformal transformations that are not well understood. There are some subtleties, for example, regardless of whether you sandwich your Dirac operator by something coming from the algebra or from JAJ, you have issues of composition. For one thing, if you sandwich by K and then sandwich by K prime, it's not the same thing as sandwiching by the product, one way or the other. And even if it were, the product of two positive elements of the algebra is itself not guaranteed to be positive. So where do you go from here? It could be that conformal transformations just don't compose in the non-commutative case, but that's a little bit unsatisfying. But we have this nice idea currently, and this is absolutely ongoing work, where instead of sandwiching, we step back a little bit and look at something a little bit more general. So now we multiply on the left by whatever, something from A or JAJ, and on the right by its adjoint. And the insight to take here is supposing that A is invertible in A or JAJ. It satisfies polar decomposition into something positive and something unitary. So now conformal transformations do compose, but up to unitary transformations. And even more so, actually, in this general case of just A coming from the algebra, from the invertible elements of the algebra, both conformal transformations and unitary transformations work within this framework in the same way. So it's like a unifying framework. But there are still a lot of questions to ask about this stuff. So for example, there was a paper by Shamsuddin Khan and von Zelekom in 2013, which talked about how if you forget about the first order condition altogether, it's possible to define a semigroup of perturbations for the Dirac operator, which generate fluctuations. And those fluctuations look like this, where we have, of course, the original Dirac operator, a one form, what I'll call an opposite one form, and then this quadratic term, which is new. And this, the motivation, just to give a bit of background, the motivation behind this is normally when you obtain fluctuations of the Dirac operator via gauge transformations. But in that case, your one form and opposite one form are built out of unitaries. And in that case, they compose. But if you want to replace those by arbitrary one forms that are still self-adjoint, it's not guaranteed that a fluctuation of a fluctuation will be a fluctuation. So if you remove the first order condition and replace it, and you can construct, sorry, these the semigroup of perturbations in such a way that now they do compose. But key to this is that your A and B, your algebra elements, basically, have to be normalized, which is no good if you want to talk about conformal transformations, because how are you going to rescale the Dirac operator if everything is normalized? So one question is there a way to extend this kind of idea without the normalization condition in such a way that captures these conformal transformations? And if not, in the spectral triple framework, but maybe also in the twisted spectral triple framework. I know there was a preprint that came out quite recently, a couple of months ago, by Martinetti and Zanchetin, which extended this result also to the twisted spectral triple case. But anyway, this is all ongoing work, like I mentioned, with Ludwig Dombrovsky, Yang Liu, and Andrei Sitash. So next section, we're going to take a little bit of a hard turn. Forget about conformal transformations for a while. We'll come back to them. But for now, we'll take a break and we'll look at Hodges spectral triples. Like I said, this is work with Francesco D'Andrea and Ludwig Dombrovsky. But before we even get to Hodges spectral triples, I want to talk about these two conditions, spin and Hodge. So what are they? So first, I want to define this non-commutative Clifford algebra. the Clifford algebra coming from the Dirac calculus as being C-star subalgebra of B of H generated by the algebra. Here, this is just star algebra A and one forms, basically. The spin condition basically says that you have some Morito equivalence that's implemented between your non-commutative Clifford algebra and the C-star completion of A. And Hodge is satisfied if the same bimodule also implements Morito equivalence between the non-commutative Clifford algebra and itself. And this spin condition, I hope, is ringing some bells if you're paying attention in section 1, because here, in the case that we have the C-star algebra of continuous functions on this side for our spinor bundle. On here, we just had sections of the Clifford bundle. So you can really see where these names are coming from. But why do we care about spin and Hodge? Well, here are the zeroth order condition and first order condition expressed in slightly different language. Here,
sorry, can you just, excuse me, can you tell me what this bar is over A in your spin condition?
This is just the C-star completion.
Ah, because A was like smooth functions, okay.
Exactly.
Okay,
so here, this is like our pre-C-star algebra, or our star subalgebra.
And you're putting it to differential forms. Okay, thanks.
Yeah.
With me, and the first condition is in fact spin C, yes? Am I right?
Well, yes. This is some subtlety which is discussed in the paper, which I don't want to get into, but yes.
Okay.
So about the second condition, so it's just Morita equivalence, I think. But so what? The Hodge condition there,
I think
so,
by the same bimodule,
which is
exactly.
H, right?
Yes.
Okay.
I mean, so I mean, of course, if you have some abstract case, you can always say that C-star algebra is more equivalent to itself. But the restricting factor is that you want it to be the same. You want it to implement both, which is not always the case. It's the same bimodule.
This is saying, in some sense, that your M is a spinor bundle. I mean, that is a spin C condition, and M, classically, M would be the spinor bundle of the manifold. You don't need spin to have a spinor bundle. You only need spin C.
Yeah, but so the reason that I'm just referring to it as spin here is because this construction really relies on the presence of a real structure. So yes, it's a spin C condition, but I mean, forgive me if I'm a little bit lax with my naming conditions.
No, I think next lines explain this. It has to be implemented by J. Okay.
Yes, exactly. So the key point.
But I'm confused about the Hodge condition.
Okay.
What happens here? You are saying that two identical things are Morita equivalent? I mean.
Yeah, as I was saying, it's always the case that in the abstract, two things are Morita equivalent. But the point is that you want this Morita equivalence to be implemented by some construction coming from your spectral triple.
Okay, so in fact, the condition is not, because I think it's a bit inaccurate. I think that indeed the condition is not that two identical things are Morita equivalent, because of course they are, but that there is some special like automorphism like Morita equivalence between them. That's what you mean, right?
Yeah, and in fact, if you give me a moment, I think I can make it much more precise what I mean by these things.
Okay, clear to me.
Okay, so like I was saying, the zeroth order condition and first order condition we've already seen. Here, omega 1D just refers to noncommutative one forms, the space of noncommutative one forms. If you take the zeroth order and first order conditions together, then what you end up with is effectively the same as saying that the real structure takes your Clifford algebra into the commutative A. But when you make this inclusion into an isomorphism, then you recover the spin condition. And this is the sense in which it's meant. So wherefore the Hodge condition? Well, in a paper by Farnsworth and Boyle in 2014, they identified that the finite part of the spectral tribble for the standard model satisfied this condition, which they christened the second order condition. And it so happens that if these three conditions, 0th, 1st, and second order conditions all hold, which is in fact true for the finite part of the standard model spectral triple, you have this inclusion here, which basically says that the real structure takes the Clifford algebra to its own commutant. And it's when this inclusion becomes an isomorphism that the Hodge condition is satisfied. So I hope that gives some clarification to my somewhat vague definition box. So now enter Hodge-Drown spectral triples. Why? Well, the Hodge condition we already know can be satisfied by finite spectral triples. So it's natural to ask, can it be satisfied by commutative spectral triples? Well, in general, for...
I go back to your previous slide. It seems to me that this M you've got there
well,
plays the
this M here is just denoting Morita equivalence.
Yeah. Oh, that's just denoting Morita equivalence.
Yeah.
But if you explicitly construct this Morita equivalence, this should play the role of a spinor bundle. Does the Dirac operator operate on the bimodule?
Yes, I believe so.
Is your condition there? Is it a there exists condition, or is it an explicit bimodule?
I believe it's a there exists condition.
Oh, it's a there exists condition. I see. Okay.
Yeah, I mean, it certainly won't exist in every case.
But if it's a there exists condition, then it's vacuous. The Hodge thing is then vacuous.
Yeah, it's the same question again. Yeah.
Yeah.
So it should be more precise, yeah, Adam. This Morita equivalence should be implemented by the Hilbert space of the spectral triple, okay, and J by a joint action of J.
Yeah.
Right. Yeah. I mean, that seems to me to have the correct feeling somehow to it.
So basically, the definition is that in the line below, right? So we take this inclusion to be equal, right? So that's the definition that you want to say.
You can take this exactly as the definition if you want, except with this inclusion replaced by an isomorphism.
I think it's much more stronger than Morita equivalence. I think it's because it's by some specific module, right?
Yeah, exactly. Yes.
Yes. Yes, as I said, it really relies on the fact that you're trying to construct this based on a particular spectral triple. So you already have a particular Hilbert space, a particular Dirac operator, particular algebra upon which these objects are built.
I suggest, Adam, to put some index subscript J on this M of Morita equivalence. Okay.
Okay. You can never have too much notation.
J of A or H.
Or H. Okay.
Okay. Maybe an M subscript J on top and an H underneath.
Okay.
I put J here.
Thank you. Okay, so as I was saying, we were interested in finding out if it was ever the case that a commutative spectral triple would satisfy this Hodge condition. So to do that, we looked at the Hodge-Drown spectral triple, which is sometimes called a Riemannian spectral triple. The reason is basically that you forget about spinors for a moment, and you take as your star algebra smooth functions as before, but instead of acting on L2 sections of the spinor bundle, now it's sections of the complexified exterior bundle. And the Dirac operator now is this Hodge-Dirac operator, where the D is just the differential on one forms. And this D star.
Sorry, I'm still confused. So you defined what does it mean for a real spectral triple to be a spin and to be Hodge. Yes, and now you give an example, a compact orientable manifold, which, okay, this does gives rise to the spectral triple, but not a real one. Yes, am I right? So.
Sorry, could you say that again?
So once again, you start with a real spectral triple. Okay, for a real spectral triple, you define what does it mean to be Hodge for a real one. And then you give an example coming from a general Riemannian manifold, which produce a spectral triple. Okay, but this is not a real spectral triple.
Yeah, indeed. Sorry, I've been a little bit sloppy.
So I'm confused.
So the
yeah, okay.
So what's important?
Or is it Adam, that actually, you know, you can state it was on the next slide that such spectral triple is indeed real with some J, and then it provides this Hodge duality. In
some sense, yes. In truth, what I have said here, that we require a real spectral triple, is not super precise. Rather, you need a spectral triple with at least some anti-unitary. I think the example will make it more clear. But
so
certainly,
for a general...
if you give me, if in the case of the canonical spectral triple, where your anti-unitary operator is really a real structure, then it's for sure spin. And indeed, in the case of the finite spectral triple, which I mentioned earlier, this is also a real spectral triple, really a real spectral triple, which is for sure spin and for sure Hodge. In general, for a spin manifold, the Hodge condition in general won't be satisfied.
Yes, but you started with something opposite. You started with a general, not necessary spin manifold, and you are saying that you have a real spectral triple. So this is my problem. This is my question, and here I'm confused.
I don't think Adam said this. He didn't say this.
But
I mean, this is, to be clear, this is not something that is following from section 1. For example, this spin condition is modeled after what I presented in section 1, but it's not a consequence.
Okay.
So, the Hodge-Durand spectral triple. The important point here is that there are two natural antilinear isometries on this Hilbert space. One is just complex conjugation. The other one is complex conjugation composed with reversal of the wedge product. This first one, C, the complex conjugation, is a real structure. It doesn't implement the Hodge condition with respect to this particular Hilbert space. And this Dirac operator, this algebra.
Okay, so sorry for asking this question. This is precisely the answer for my question. This slide clarifies.
Okay, yes. In fact, I thought maybe that might be the case. So, as a minor point, C actually, if you redefine C to include the grading, this grading here, this is just charge conjugation from section 1, as per usual. But that's not so important. This J here is another antilinear isometry, another anti-unitary. It's not a real structure, but it does implement the Hodge condition. Why is it not a real structure? compared to the definition I gave earlier. The main reason is that it doesn't commute with the Dirac operator, which you compute very, very straightforwardly. In fact, on the Hodge-Drown spectral triple, there are two kind of natural definitions that you can choose for the Dirac operator, and this takes you from one to the other, which is in itself kind of interesting, but not what we want. So, but the point, I guess the punchline of all of this is that if you choose a particular twist operator, like so, where k here is the degree of the form, then this twist operator along with j gives you a twisted real structure. So we have the correct commutation for a twisted real structure with nu jd, dj nu. The semi-twisted first order condition is not a problem because actually this twist is mild, which is to say that it's the square, conjugation by the square of the twist operator is just identity. So the semi-twisted first order condition just reduces to the ordinary first order condition, which J does satisfy. And incidentally, it's also regular. And as far as the grading is concerned, everything commutes. So there's no problems there. In fact, this spectral triple will always have KO dimension 0. So I think that was it for this section. If there are any more questions, maybe now is the time before I escaped section 4. Oh yeah, sorry, one more point. We also computed explicitly for the example of the torus. And we found that there's no real structure. When I say real structure, I mean in the traditional real spectral triple sense that I gave before. There's no real structure that implements the Hodge condition on the Hodge-Drown spectral triple for the torus. But as we already showed, a twisted real structure does exist and can be found. Okay.
So perhaps you can say that this definition of a Hodge condition for twisted real structures, for spectral triples with twisted real structure.
Well, yes, if you like, we can start off requiring that we have a twisted real structure. Okay, well now I'll move on to the topic of gauge transformations. So, as I mentioned earlier, in response to one of Piotr's questions, one reason that having a real structure is very useful is for the purposes of gauge theory, where it plays a very important role. So you can imagine that tinkering with all of the definitions is going to have some impact there. So in this section, I'll talk about how you normally approach gauge theory in Con's approach to noncommutative geometry coming from spectral triples, and then what goes wrong and how do you fix it. So normally we start off with a real spectral triple. Again, a really real spectral triple. We take some abstract, full finitely generated projective right Hilbert A module. This will automatically be root equivalent to A-valued endomorphisms on E. Because we have a spectral triple, we have a Hilbert space that our algebra is represented on. So we have that the endomorphisms of E actually act on E tensor H, which is itself a Hilbert space. So since this is a Hilbert space, we would like to extend the action of D just from H to E tensor H. But in order to do this, you need to introduce a connection. A connection here is something which takes elements of the module to the module tensor 1 forms in such a way that it satisfies the Leibniz condition, where here this delta is some derivation which generates the 1 forms. The reason that you need to introduce the connection is because if you don't, it's reasonably easy to see that if you just hide this term here and insert some A here or A here, the tensor product won't be balanced because the Dirac operator doesn't commute with the algebra. So you need this connection to scoop up the extra terms. Now, if A is Mood equivalent to B, then B is Mood equivalent to A. So we can do the same procedure, but with a left Hilbert A module, which here, for the sake of argument, we'll take to be the conjugate module. And then we have the same story, but with everything flipped around. So we have endomorphisms acting on H tensor E bar. We extend D to H tensor E bar in the exact same way, where here now we have a connection which I'll call an opposite connection, by which I mean now we have one forms which take values not in the algebra, but the opposite algebra. So we recognize that left and right Hilbert modules are compatible. That is to say, we can just string them all together and we get a perfectly respectable action for the Dirac operator. We have the term that just comes from the Dirac operator acting on Hilbert space. We've got our connection acting on this side and our opposite connection acting on this side. So recall that our module is finite projective. So we can just say actually that it's equal to the algebra, that it's just the same thing, E and its conjugate. And in that case, the particular form that the connections take can be computed. It's relatively simple. You get a commutator of, say, for the action on A, commutator of D with A plus some arbitrary one form times A, and a similar thing in the opposite case, but now everything gets conjugated by J. So this is how you end up with fluctuation, which is kind of what I was hinting at before. You get D goes to D, it's D plus some one form plus what I'll call an opposite one form, which is just a one form conjugated by J. And very key ingredients, the reason that the real structure is so important is that you want the right action of the algebra to be given by conjugation by J. Remember that the zeroth order condition takes the algebra to its commutant. So this is how you make sure that the left and right actions are compatible. So take a step back. We want to talk about gauge transformations in particular. Gauge transformation is the action of some unitary endomorphism on the module. In the case that our module is just the algebra, we can identify the gauge transformations as in particular coming from unitary elements of the algebra. And you compute through everything, and this is more or less what you get. So adjoint action on the Hilbert space, this is standard stuff, same for the algebra. The one form takes this slightly more complicated form, but again, this is quite standard and in fact, exactly what you get in the commutative case. And the Dirac operator, the way that you define the gauge transformation is basically saying that the gauge transformation of the Dirac operator is the Dirac operator with its one forms gauge transformed according to this rule, which is not to say that if there's no fluctuation, nothing happens, because of course, if alpha is 0, we still pick up these extra terms. And that's basically the pure gauge for the Dirac operator. So that's all good and well for the regular case, but we're interested in twisted real structures. And you can already see that something's going to go wrong, because even if the original Dirac operator has the right commutation relation with nu and j, the fluctuation, the pure gauge fluctuation won't. So, I mean, this is the simplest case for a gauge transformation of the Dirac operator. If that fails, we've got a real problem. So what do? So we know reasonably well what we want. We want something that looks like this, where we're now sandwiching our opposite one form by our twist operator. And then for sure, this will be satisfied. But do we have to insert this at the end in some ad hoc way, or can we get it via the procedure that I showed before? Well, to answer that, the first thing we have to observe is that what I'll call a twisted opposite one form, which is a one form conjugated by J, sandwiched by nus, is really a twisted one form in the sense that the commutator with the Dirac operator is twisted by the automorphism coming from the twist operator. Slightly unusually, the algebra, the opposite algebra element conjugated by J includes the twist. So we have these kind of unusual representations. But remember that this is an automorphism of the algebra, so we're still in JAJ, everything is fine. So what do? Well, the first slide that we looked at, nothing changes. We're still dealing with spectral triples. But the second slide, where the real structure enters, now we have to start making alterations. The first change we have to make is that our opposite connection is replaced by what I'll call a twisted opposite connection, which is just as before. We replace the space of opposite one forms with twisted opposite one forms. And this we have to compose with some twist, the reason for which I'll come to later. So again, left and right module structures are compatible, string it all together. This passes through, set E equal to A, compute the operator forms. And indeed, we end up with exactly what we want. Where now, important point, the right action has to include the twist. So this last step kind of skips a lot of details. So I'll give a bit of a proof of where this comes from. The important point is that the requirement for this twist here, this comes from needing that the Dirac operator be well defined on the expanded Hilbert space. And this was something in my paper with Ludwig, which we kind of adapted from an early paper by Landi and Martinetti, which did the same thing for the real twisted case. But of course, they did it for, let's say, the first slide and the second slide, because everything there was twisted. Here, we're kind of trying to make the puzzle pieces fit together. So we're taking only the twist that's relevant to the opposite part, the part with the real structures. So first, we have to choose a particular right action which incorporates the twist. Then we define a derivation, which I will call a twisted opposite derivation, just for the sake of not having to rename 100 different things. But this is really a derivation, not a twisted derivation. It's a derivation, but it's so because we've chosen a very particular choice of left and right action on the bimodule of twisted opposite one forms, which is given by this. So this generates a connection, twisted opposite connection, which satisfies ordinary Leibniz rule with respect to this derivation. We extend this to the Hilbert space in the most straightforward way. And you can see that incorporating this twist solves the issue of balancing the tensor product. So, but why this twist here? Basically, the reason is that you can see from before, sorry, I'll try to be as explicit as possible. This twisted one form connection, whoops, comes, well, it comes from here. Oh God, now I'm getting lost. Well, the point is that much like in the other case, you get a derivation plus an arbitrary one form, where this one form is your connection one form. So once you have that, it's just a case of plugging it in and chugging through. And this I really will spare you because it's quite dry. But the end result, which is the most important thing, is that you get the Dirac operator plus your arbitrary twisted opposite one form. So this is exactly what we were after here. Okay, so first question, does this make any sense? Well, remember that since we're still working with one forms, the one forms have a set fixed gauge transformation given by God. So we can conjugate by J, sandwich by the twist, to get something which we expect should have some meaning from the perspective of the construction that we've just given. And indeed it does. It turns out that this is exactly equal to an arbitrary twisted opposite one form. Well, actually the twisted opposite one form coming from this alpha, so it's the same one, but with U and U star acting again with this unusual action coming from the bimodule of one forms. And the same thing happening over here, where now we have this derivation. And this, if you compare this to the rule we have for gauge transformations of one forms, it's the same. Where here the derivation is just commutated with D. So this makes sense. Good. But now that we've introduced a new right action, conjugation by unitary elements is not just the familiar uj, but the twist gets incorporated here. So let's call this operator V. And for the sake of future convenience, we'll also define U, which is basically the same thing, but with the opposite choice of twist. First thing to note, neither of these is unitary in general, which might raise some alarm bells, but it's okay. It's okay. Using the fact that we've got these particular operators implementing our gauge transformations, we can ask how they act on the other points of interest. Unfortunately, I can't see the top of my screen, so I have to refer to my iPad. But okay, so yeah, using our V and W, the gauge transformation of the algebra, straightforward. Conjugation by V, conjugation by W, same thing. Perfect. Gauge transformation of the Dirac operator, a little bit more unusual. Multiplication on the left by W and on the right by V inverse. So there's a mismatch now, but okay, that's not too bad. Where things get really weird is when you consider the twist and the antiunitary, because you would like that they're invariant or covariant individually. But if all you're playing with is V and W, doesn't happen. Instead, what you get is that nu J together as a block is invariant under conjugation by W, and J nu is invariant under conjugation by V. It looks like they should be able to satisfy individual conditions. So if you insert in here, if you can imagine inserting a V inverse V, and here inserting a W inverse W, you could see how actually you could have nu equals W nu V inverse and J equals VJW inverse. But like I said, in general, it doesn't happen. So now let's make some observations. First of all, we were worried about V and W not being unitary. When are they unitary? Well, when nu is unitary. So that's something we might want to be interested in. Furthermore, when do we have that nu and J satisfy these separate conditions that I mentioned? Well, precisely when nu is unitary and self-adjoint. But if nu is unitary and self-adjoint, then V and W are actually exactly the same. So it seems like nu unitary and self-adjoint is really what we want, but it's also very strict. It's very restrictive. There are not going to be a lot of operators which are unitary and self-adjoint in any case. So, okay, let's see what we can get away with. First of all, the Dirac operator in general, once we take the gauge transformation, it's not automatically self-adjoint because of the presence of the twist. So what we want at least is to take the twist to be self-adjoint to ensure that the Dirac operator is self-adjoint, that its gauge transformation is self-adjoint. So that's basically non-negotiable. So let's assume that the twist is self-adjoint up to sign, because usually it appears twice. Well, what we want, if we're doing gauge theory, we're not just interested in the kinematics, abstract geometrical stuff. We would also like dynamics. We would like to do some physics, ideally. So to do that, we need action functionals. And the way that we get them, there are two. First is the fermionic action, which we normally obtain via this bracket here. But the issue is that now it's not symmetric or anti-symmetric anymore, because normally if you want to show that this is symmetric or anti-symmetric, you rely on the fact that D commutes with J. Not true anymore, because the twist is involved. So we need to tweak this bracket. The correct modification is to include the twist here, or on the other side of J. In fact, both choices work. And not only does this give it the right symmetry properties, but it also ensures that the bracket is gauge invariant, which is super important. So once it's symmetric or anti-symmetric and gauge invariant, we can use it to define the fermionic action function. Where here, the tilde is over the side just means we're taking the Hilbert space elements, the relevant ones, and Grassmannized. So it seems like the twist being self-adjoint is going to be enough. But we run into an issue. So suppose we just we have some Dirac operator acting on an eigenvector, and we take the gauge transformation. Ideally, we should get just the gauge transformation back, but we don't. What we find is that rather than getting lambda v psi, remember that v is what gives the gauge transformations for Hilbert space elements, we get w. So the spectrum is different. And this is a problem because, of course, we're talking about gauge transformations. So if your gauge transformation is affecting the spectrum, you're going to have some unphysicality. In fact, it's very explicit from the perspective of the bosonic action, where your trace is picking out eigenvalues from the spectrum of the Dirac operator explicitly. So this is no good for physics. How do we solve the problem? Well, we already know. The problem is that v is not equal to w, but we know when v is equal to w, it's when the twist is self-adjoint and unitary up to sign. And in principle, these signs can be different. So at least if you want to do dynamics, it seems like having the twist be unitary as well as self-adjoint is unavoidable. So it goes. So that's the portion on gauge theory. Okay, so now I'll move on to some really recent stuff, which is twisted real structures for twisted spectral triples. This is unpublished work. I'm afraid that the title of the section has kind of given away the surprise, but okay, for the sake of theater, let's start with an example. So we'll consider the example of two-dimensional Kappa-Minkowski space, where for the algebra we take Schwartz functions on R2, for the Hilbert space L2 functions on R2 doubled. The Dirac operator will be given by this. I'll explain what it is in a second. And also it's twisted. Note that we're taking Schwartz functions here because actually, technically Kappa-Minkowski space, or at least this implementation, is not compact. But for the purposes of defining a spectral triple or twisted spectral triple, the number of things that you have to change is not large. So for practical purposes, just assume that everything I said before still holds. Okay, so the representation is given by this mess. The Dirac operator in particular, this kappa here, is the kappa of Kappa-Minkowski. This is our deformation parameter. T here is a generator of translations in the zero direction, and P is the operator, the momentum operator in the one direction. These gammas are just the two-dimensional gamma operators, gamma matrices, and the twist is implemented by the modular operator.
Excuse me, also
yes.
Representation pi under the integral sign. Is it okay? Or
sorry?
You have a pi, a representation pi under the integral sign. Is it okay? Here. Okay, thank you.
Ah, yeah, sorry, that's a typo. That's yeah, that shouldn't be there.
Okay, and calligraphic F0 is what? The Fourier, yes? Fourier
yeah, Fourier transform, but just on the zero direction, zero component.
Okay.
So what's the, is this the Heisenberg representation like that? Is it indeed a representation, or like if it comes from the Heisenberg, should be sort of a projective representation?
So this representation, I'm not sure what you mean.
So this representation seems to induce from a action of R2 on R2, right?
Yeah.
And then what's this action? For me, it looks like this Heisenberg representation is like one Rx by translation, the other Rx by multiplying a character like e to the I by something. So do you have a name for this representation? I mean, I think this is.
I don't know actually.
No, it should be just a representation. I think should be just. Should be just a representation of this commutation.
Yeah, I believe it's just a representation. As I don't know if it has a particular name, but it's certainly a kind of, I don't want to say twist again, but it's some modification of the standard action of R2 on R2 for sure.
Okay. Mm.
But yeah, I mean, truth be told, this is not something I'm expert in, Kaplan-Minkowski space. And the details are quite hairy.
Sorry, Adam, but I'm still confused as to how to read this expression over here. So, okay, pi is gone. We erase it.
Yeah.
I understand I should get something like, which is like a function of two parameters, p0 and x1. And I understand that that f that we are taking is an element of your algebra as R2. Am I right?
Yes.
Okay, so this is a function of two variables, and these are my two variables. Fine. Okay, so please tell me again what this f0 means. Is it acting on f? Is it? I don't understand this part.
Yeah, I mean, this f0 is really the Fourier transform of f.
Ah, so okay, so it's just f0 of f. Okay, okay.
Yeah, exactly.
Okay, okay. So this part
but the Fourier transform only with respect to the zeroth variable.
Yep. Yeah, it has two variables, so it makes sense. Okay, thank you so much.
Yeah, so sorry, the twist. The twist is implemented by the modular operator delta omega, which is, for all intents and purposes, just the operator which implements the modular automorphism one parameter group. And here omega, this omega, which is referred to everywhere, is the KMS weight, which is used in the construction. So the relevant point comes from a result of a paper by Metasse in 14, which shows that this formulation of Kaplan-Minkowski space admits a particular anti-unitary operator, J, where, okay, this star here is given by this, and this sigma omega I over 2, this is an element of the modular automorphism one parameter group, where here the parameter is being evaluated at I over 2. Basically, this is just, again, related to the modular operator. But the details are not so important. What's interesting is the properties, because it looks very much like a kind of modified real structure. So everything is normal, apart from the fact that the commutation with D includes this factor of the inverse of the modular operator. And the first order condition, or whatever you want to call it, this modified first order condition, is of course twisted on the inner commutator, because this is a twisted spectral triple. But there's no twist on the outer commutator. So let's say from the abstract perspective of someone who just wants to twist everything and see what happens, it's quite natural to propose some kind of definition like this, if you were a masochist, for example. So you take a twisted spectral triple, AHD with a twist row, some automorphism of the algebra. You define an operator nu on the Hilbert space, which gives you a different automorphism of the algebra, some antilinear isometry J with a compatibility with the twist row. Then your new twisted real structure is, as before, commutation of D with J with nu included. Zeroth order condition unchanged, regularity as before if you want it. And the first order condition, what's sitting in for it at least, has a twist on the inner commutator and a different twist on the outer commutator, where this one is the composition of the twist coming from rho and the twist coming from nu. So we're just twisting everything here. And of course, again, if there's a grading, we have some compatibility with the grading, which we're not so interested in. So this is kind of like a doubly twisted first order condition. But of course, we can always set one of these twists to be the inverse of the other. And if that happens, what you'll get is not a doubly twisted first order condition, but a kind of half twisted first order condition where you have a twist on the inside and no twist on the outside, which looks an awful lot like what's going on here. So it turns out that for this example, this is precisely something you can do. And the twist that makes it all works is just the square root of the modular operator. And what's especially interesting about this is that unlike all of the previous twists we've seen, this twist is unbounded. It's still densely defined, coming from the definition of the modular operator. but it's unbounded nonetheless. Of course, by definition, we have that, let's say the conjugation by this twist is an automorphism of the algebra, so we have no problem with boundedness here, which is really the important thing. But it's a nice result in any case. I think that's all I had to say on that topic. So now I'll move on to the final section, multi-twisted real structures. This is based on work by Ludwig Dombrowski and Andrei Sitash. So suppose you haven't had enough of twists yet. What if you took your Dirac operator and decomposed it in some sensible way into parts? And to each of these parts of the Dirac operator, you wanted to associate a twist. What you end up with, more or less then, in that case, is a multi-twisted real structure. So as before, more or less what we're doing is taking all of the relationships we had before and just doing them by parts. So now we have I-many commutation relations for the I parts of D and the I multi-twists. We have I-many regularity conditions if we want them. But now things get a little bit hairy because actually the case coming from examples which are most interesting, having a twist which is an automorphism of the algebra is a little bit too restrictive. So take a step back and only implement automorphisms of bounded operators. But then you need to implement not just the zeroth order condition, but you need to incorporate the twists. In particular, you need to incorporate the twist going one way and its inverse on the other side. And again, we have I-many twists, so we have I-many conditions. And again, the grading compatibility conditions and so on. So why would you do this? Well, the nicest example, or at least the example which could fit on a single slide, comes from the asymmetric torus. So this is an image of the standard commutative torus. I mean, this is the normal torus, and this is the asymmetric torus, which has a torus with curvature. You can promote these to, well, let's say, generalize them to a non-commutative setting, in which case you get a non-commutative torus and a non-commutative asymmetric torus. And it turns out that you can obtain the asymmetric non-commutative torus by performing a partial conformal transformation. So if you recall from way back in section 1, I mentioned there was this Dirac operator on the non-commutative torus with these two derivations. Well, here we're just leaving one direction untouched and the other direction conformally transformed. It always comes back to conformal transformations, something or other. I wanted to mention some more stuff, some final remarks. There was a talk recently, I think last week, by Koen van den Dungen about a paper preprint from last year about localizations of the Kasparov product in KK theory. And he had some interesting stuff where the Dirac operator or the Fredholm operator ends up getting sandwiched by these operators which come from an approximate unit, so positive. And in fact, Koen pointed out that this looks like a kind of conformal transformation. But his operators were acting like a partition of unity. So this is kind of another way to think about partitioning the Dirac operator that's maybe not quite as blunt as exploding it like this. Also, something that Koen mentioned was a preprint he did in 2014 with Fatizadeh about taking products of two tori to give four torus with conformal structures. And I also wanted to mention that there's a lot of work being done, which I have no understanding of, I'll say right now, but that tackles conformal transformations from a completely different direction, where you don't leave the Hilbert space untouched, you tweak the Hilbert space, and then the Dirac operator has a different form and so on. So to, I guess, take us full circle, there's still lots not understood about conformal transformations that we're still trying to understand through all sorts of various means. In particular, I think approaches like this with multi-twists or twisted real structures, twists of twists, and so on, can hopefully provide some insight into this and also other stuff. That really is everything that I had to say. So thank you very much for your attention. And I'm happy to take any questions. Oh, sorry, one final point. Everything that I've mentioned, hopefully, or forgotten to mention at least, are here in the references. So if anyone wants to go back to the recording and check any of that out, be my guest. Okay, now I'm done.
Okay, Adam, thank you very much. So let's clap hands. And let's continue with questions or comments. How about co-authors, Ludwig, Francesco? Any further comments?
Make a very short comment that actually what Adam said, this is more than conformal transformation of the, okay, the non-commutative torus you could understand as, let's say, twisted product of two circles. It's algebras of two circles. But this coefficient k is not depending only the second variable generator of the non-commutative torus. So it's not really conformal transformation of the second factor, let's say, okay, coming from the second factor, from the second generator, but k depends on both. So it's still more than just product of two conformally transformed, let's say, non-commutative product of two conformally transformed circles. Okay, say it like that. So it's and this fits this multi-twist instead. So there are even more general transformations which fit to twisted real structure, which are more general than just product of two conformal transformations.
Okay. Anybody else? Tomek?
Yes, I have a question. Could you come back to this Hodge condition?
Yeah.
Yeah. So there are very important differential operators of the form d plus this d star or d minus d star multiplied by minus I, and they play a role in two important Atiyah-Singer index problems: the problem of Euler characteristic and the problem of the signature of a manifold. So yes, so you have different grading. So this grading probably is for this Euler characteristic.
Yeah.
Yeah. What about the signature operator?
So in that case, yeah, there is another grading, and that's the grading that comes in even dimensions from the Hodge star.
And what about this real structure twisting?
In that case, I think we didn't. We talked a little bit about this other grading, but it's not really intimately related to the twisted real structure, or the stuff that we investigated with the twisted real structure. I think actually, speaking off the cuff, there's a little bit more to be said actually on that topic. But it's one of these things I never got around to looking into in a lot of detail. But yeah, for what we talked about in our paper, this stuff with the twisted real structure really only requires, we only look at the case where the spectral triple is equipped with this particular grading, the one coming from the degree of forms.
Okay, so the second question would be about this.
It is also okay. Now I forgot a little bit. Perhaps okay also for the other Hodge star grading. I think it's also
okay. Okay, I have another question about this operator. So d plus d star or minus I times d minus d star, they are both particular cases of combinations like, let's say, ud minus u inverse d star, where u is of absolute value 1, the complex number of absolute value 1. Can you deform all these considerations along these one parameter deformations?
I really don't know, actually. It's the first time that thought has even come to mind. But it's an interesting question.
Okay, thank you.
Richard?
No, okay.
No. Anybody else? Yang?
Yes, so these two gradings, J and C here, basically they don't require the spin structure, right? So it's just
You mean these two?
right, yes.
So yeah, something which I kind of glided over is that I said we kind of ignore the question of spin here. But of course, in general, if you want to define your Dirac operator, you need some spin-C structure anyway.
Oh, no. I mean,
But
okay.
but the point is that it's a real spectral triple for C. So in that case, you get something which is spin. And it turns out that this will basically be equivalent to the canonical spectral triple with some extra work needed to fill in the gaps. This Dirac operator will be, for example, exactly equivalent to the standard Dirac operator. But I don't think that's the case for J, at least.
No, even with C is not the case, but you could probably understand these differential forms as probably some symmetrized tensor product of spinors. You can construct differential forms. So twisted spinors, but twisted by the.
Yes, I understand. I mean, this part, I mean, for like a Dirac type operator, in general, you don't require this, you know, the spin structure. I mean, for the specific, like a spinorial Dirac, in which, so the tricky part is that for spinorial, you lift your Riemannian connection to the, you know, to the spinorial, like to the spin group, right? The Lie algebra of the spin group. There you need a spin structure. But if you don't use that connection, everything is fine. I think just for the Riemannian structure, I mean, you don't need to assume the spin condition. But I think the point is that I mean, without the spin condition, we can still have examples of real structures, right? Like you mentioned here, C, right? So with this AH and D, right? So it's still, you have examples of real spectral triples, right? So without the spin structure.
Well, indeed, apparently so, yes.
Not even spin C, you don't need even spin C here. But actually they were studied, but not so much from the point of real structure. So there is some mentioning about Tomita Takasaki in a paper by Lord Rennie and Giovarilli. There is a paper already some time ago, a few years ago. So this spectral triples were already studied, but not from the point of view of the Hodge condition and real structure. Okay.
So another small question. So you are using D minus D star, right? I mean, I remember it's usually D plus D star or something. And I mean, is that some?
Yeah, you can take either choice, really.
Question what D is, right? What is D? Is it D by dx or is it I D by dx, right? It just depends whether it's self-adjoint or skew self-adjoint. Right?
Okay.
It depends for the signature of your spin structure.
Yeah.
Or your Clifford algebra. So it's plus or minus.
No, but okay, actually there are two different operators, but maybe there is even one parameter family, as Tomasz Maszczyk is suggesting. I never seen this actually, but probably. And these two particular come from the Clifford multiplication on there is the one differential forms is a Clifford module, but they come from two different actions, from left and from right of the differential forms. So this corresponds to the natural Dirac operators coming from the Clifford module, but they are not spin, of course, not coming from the representation of the Clifford algebra on the spin representation of the Clifford. This is another irreducible representation, of course.
Okay.
No, so the one Tomasz was talking about, it's essentially the same as this one. Just conjugate by a constant invertible matrix. If you want to put these phases lambda conjugate on the ND star, you just conjugate by invertible diagonal matrix with constant coefficients. So the structure is isomorphic completely.
Yes, but it depends on the choice of the second grading. So the interplay between this twist and its choice of
No, because
you
just conjugate everything by the same.
No. They are not completely conjugate. For instance, the signature operator is not a conjugation of the Euler characteristic operator.
That's not what I'm saying. No. Of course they are different. But what I'm saying is that you can replace d star by lambda conjugate d star and not doing anything. That's all I'm saying.
Not entirely, because in this, could you come back to this conjugation, interchanging d plus d star? Yes, precisely this at this place. So this J operator interchanges these two type of operators. Of course, they are equivalent up to this constant transformation, but from the point of view of the action of J, they are not.
You conjugate J as well. You conjugate everything.
Yes, but
your J will be different.
Okay, you can, but they are still not the same.
No, isomorphic. So the whole structure is isomorphic. It's not the same, of course, but it's isomorphic. That's why nobody thinks about it.
So I have a question to the lecturer. Can you remove this inequality in the last line by some constant transformation? Because I see a problem here, this yellow inequality, yes.
Yeah.
If this is a problem which can be resolved by some constant transformation, so.
No, not that one.
So I'm talking about these problems, which cannot be solved by
but you said replacing d by lambda d, right? That's what you said, right? D by constant times d. That's what you said.
Yes, so these two differ by such a transformation. Minus I times d, yes.
No, you change both of them at the same time. It's both sides change. You don't change it to one side and not the other.
No, I'm not talking about this. I'm talking about this. If you take d plus d star and minus I times d minus d star, they are differ by a phase applied to d. This is true. But they are different. And
what phase? Yeah.
This phase of absolute.
So and.
But they are different. So changing one, you are changing another by changing the phase, but you cannot make them at the same time equal.
No, but nobody says you can.
I'm talking about this. I'm talking about this structure when these operators, although they are can be transformed one to another by some transformation with constant coefficients, but they are different. And if you use this phase
sorry,
to D
sorry,
at every
Thomas.
place.
Thomas, sorry. How do you
not
translate
change
D
the
plus
start,
D
this
star to D
inequality.
minus D star?
Sorry?
How do you transform D plus D star to D minus D star? How do you do that?
I'm multiplying D by a phase.
Yeah, and when D star gets multiplied by
And I'm
corresponding
forming,
phase,
and I'm
how
forming,
do you get the difference?
No, and I'm taking the self-adjoint part of this.
But then you are doing something else, right? You are not just changing
Something
the
else
phase.
that what?
You are picking up, you are changing the phase and then taking self-adjoint part, right?
Yes.
You are not just changing the
Not
phase.
changing, not affecting the Laplacian. It's this kind of transformation. So the point, my point is that these two different operators appear at the same time in this formula. So I cannot twist everything by the same constant transformation to make them equal.
Yeah, of course not.
Yes.
That's
so,
kind
so
of obvious,
this is my
right?
point. This is my point.
Okay. But you asked whether you go what's
Anything
happening
else?
when you
Anything? I'm talking.
No, but you ask
precisely
what's
about
happening when you take a phase transformation.
Yes. So
D.
this. So
and
these
statement
two are,
is nothing. You get an isomorphic structure. You can't change it one place. You have to change everywhere. If you change D by lambda D, you get isomorphic structure.
Yes, it is true.
So that's all.
Not all. I'm talking about using different operators from a one-parameter family. And sometimes they appear in a single formula. This is different from that, but
they don't. It's the same operator. It's not two different operators that appear here.
No. One is transformed from another, taken from another by this constant transformation. But there are some formulas where they both appear. Of course, you can change both by the same transformation. You obtain an isomorphic problem, but still you have in a single formula two different members of the same one-parameter family. Okay. So you could take another two members of the same family and take another J. Maybe it's possible, maybe not, but it's not so clear to me.
Well, you just rotate J, you rotate everything. Okay, Thomas, I don't understand the question.
No.
What is your problem? What are you trying to say?
I doubt.
What are you trying to say?
Okay, there is a one-parameter family of self-adjoint operators which can be obtained by taking the self-adjoint part of D multiplied by a constant complex number of absolute value 1.
Sure.
And there are formulas where two different members of this family appear at the same time.
Where?
Okay, you can twist both.
Where do they appear?
In this formula. Can you see this formula? I have to use annotate.
Yeah, but as far as I can see, it's the same operator, right? It's the same D.
No. So Dirac here is D plus D star, and here is minus I times D minus D star. This is not the same operator. There are two different operators from the same one-parameter family.
Let's.
Okay.
Let's try first. No,
and
Thomas.
I see the problem here.
Thomas, no, it's a DD star appears 2x2 matrix.
By the way, I should add that there is also gradient there. Therefore, both sides are self-adjoint. So there is also gamma on one side, but it anticommutes with D and with D star. Okay.
Mm-hmm.
You should always think of D as being a 2x2 matrix, of diagonal 2x2 matrix with respect to some gradient. These the Dirac operator is a 2x2 matrix, self-adjoint 2x2 matrix, and this D here is one of the corners.
Yes, but they are different.
What do you mean they are different? It's the same D on both sides. As far as I can see, it's the same D that appears on both sides of the formula.
You see the same D, but these blocks are different. this self-adjoint part of D and self-adjoint part of minus ID, they are different. I'm talking about this. I cannot see the point of your objection, because
Those are not the blocks. Blocks are with respect to grading, as far as I understood, yes?
Not with respect to grading. Come on, there's a grading involved here.
So the blocks are taken with respect to grading.
But these two blocks are different and they appear in the same in the single formula. So my question was, can I independently take here some other operators from the same one parameter family?
Well, you could take up some other operator which has nothing to do with this family, and if you want to.
Yeah, so my question
you want
was,
to take different operators, sure.
So
both
my
sides
question,
are no, Thomas, as Ludwig said, both sides are actually what, self-adjoint, right?
Yes.
Because of a grading, appropriate grading.
And
so sure, of course you can make them equal. If you choose appropriate D on one side and another D on the other side.
No, D is fixed. It comes from the de Rham calculus. But I'm
as you know, and as the RAM calculus, D plus D star and D minus D star are quite different operators, right? You can make D minus D star self-adjoint by multiplying by, well, this thing lives in some 2 by 2 matrices and multiply by skew self-adjoint constant matrix. And now it will be self-adjoint, right? That's what happens here. But of course, operators will be always different. It doesn't matter how you rotate them. Doesn't matter if take D plus D star or lambda D plus lambda D star.
Okay, guys, I think it's getting out of hand. Why don't you discuss it later on using a whiteboard? Because I think
I don't know. No, if you want to change it, take another one. Then sure, of course you can make it equal for different operators. For that, you don't need rotation. If you have D1 on one side and D2 on the other side, of course you can make them equal if you choose them appropriately.
So I feel to be far and far from my question.
Yeah, but answer the question. What's your question?
So my question was very simple. Can I use here some arbitrary two members of this one parameter family, or these two are related by something special transformation with respect to the de Rham calculus? Is this equality significant from the point of view of the de Rham calculus, or I can take completely two different members of this one parameter family? This was my question, in fact.
I think this inequality. Okay, Adam, that's your lecture, right?
Yes.
Sorry, but
theoretically.
So okay, question to you guys. So this inequality isn't just the fact that gradings are completely different.
So I guess it's not, because this this operator actually comes from this comes from Clifford action, right? I know probably.
Yeah, sure.
So that's
you
why
mean gamma, yeah, or nu or whatever it is.
So it's
nu, right?
like the construction of Dirac operator is right. You take a Clifford connection and then you contract with Clifford action. So so then here, so if we choose the standard Clifford action acting on differential forms, in particular, so this Dirac operator in particular agree with D plus D star or D minus D star, depends on the convention. So that's why probably, so we don't have this sort of flexibility, like you add one phase in D, right? So the other.
Okay, so this answers my question.
Right. So
yeah. There's some rigidity of the choice of this pair of these two operators
Yeah,
Okay,
yeah.
no,
I mean,
yeah.
actually, so right, that the Clifford action is important, right, behind the construction of the operator. Okay.
It's interesting because I know that these two operators, these concrete two operators, provided the Laplacian is invertible, then they play a role of quaternionic units and they anti-commute. Okay, you can cook up quaternionic units from this. So this must be somehow related to the very rigid structure of Clifford algebras. So I suspected this. So thank you for your
Okay,
explanation.
so maybe I just add small comment to Tomasz and well, perhaps Richard. I don't know if they understood properly each other, but so these two are really coming from two Clifford actions. But what are these Clifford actions? These Clifford actions come from the isomorphisms as vector spaces of the Clifford algebra and exterior algebra, but only as vector spaces, not as algebras. But when you use this isomorphism of vector spaces, so treat, let's say, exterior algebra as a module over Clifford algebra, this comes from this vector space isomorphism from two operations on the Clifford algebra on itself. Left Clifford multiplication and right Clifford multiplication, which are not common. So when you transport these two actions to the exterior forms using this isomorphism as vector spaces, you get these two operations. Well, you get two operations on the exterior forms and you contract it with the usual derivation, okay, so connection, and this provides these two operators.
You mean left and right? Okay. So you mean left action and right action?
Exactly.
That's what you're saying.
Yes.
Okay.
Yeah. Good.
Okay. I think this was quite a lengthy discussion, but if somebody still has a question to the speaker, well, go ahead now. Well, Francesco raised his hand, but he had to leave before he had an opportunity to ask his question. So I don't see any other raised hands. So let me just finish with asking you a very elementary question. Can you go back to the gauge slides?
Yeah. So.
Yeah, just go ahead. I will. Yes, go. Yes, stop. I want to see how you have. So when you want to have a gauge transformation on a finite and projective module, it's just some unitary automorphism, right? Of a module.
Sorry, say that again.
When you want to have a gauge transformation of a finite projective module, then when you defined it simply as
exactly.
the unit. Oh, here it is. Oh, here it is.
Yes.
This is what I was. Yeah, but okay, it's a unitary endomorphism, so it's a unitary automorphism because it's invertible. Okay, and so now how does it act on a connection, this gauge transformation?
So once you have represented everything as operators, the connection one form transforms like so. I mean, this is effectively the gauge transformation rule for a one form. Okay. And of course, here we're assuming our one forms are self-adjoint.
Okay, so I somehow think it should be, Ludwig knows is my obsession, that it should be compatible with what you've got when you are talking about projective module associated with, say, compact quantum principal bundles. And then you can simply view these guys as cotensor products. So here's your algebra of a principal bundle. Here's your, say, vector space, representation vector space, and you form a cotensor product with your Hopf algebra structure. And when in the Hopf algebra theory, Tomek Brzezinski left, unfortunately, I'm afraid. well, you have a number of ways of, you can be stricter, it can be looser, but definitely what you will have at a gauge transformation will be an invertible map, a bijective map from A to A, which definitely, no matter what you say, it will preserve two structures. It will be a map of B modules, where B is the coaction invariant subalgebra. So sorry, this is a bad notation because this is your A. Sorry, this is your. I apologize. I should put something else here. Let me call it P, because your A is the fixed point subalgebra. So this was not a good idea. So this is P, and now your A is simply.
Alek, ty już skończyłeś? To co, wskoczymy jeszcze na spacer, czy już masz dosyć?
Ludwig, we can hear you.
Chodźmy szybko. Sorry, no.
Okay. Yeah. So that's just the fixed point subalgebra. Okay, the base space algebra, and the gauge transformation will be a map from P to P, which is H equivariant and A linear. And because H equivariant, you can apply it here to this cotensor product with identity on the vector space, and it will make sense because of H conjugate. And this will give you precisely this kind of stuff that you have here. The only thing is that, well, here you demand it to be unitary, so you rarely care about the star structure, but you can also implement it, I believe, here at this level of non-commuted principal bundles, and then the gauge transformation as is studied in quantum principal bundles will give you precisely this kind of a gauge transformation as you have it here, which goes back to Kohn in 1980, whatever. This is a very old definition. And by looking at this formula for the gauge transformation of a connection one form, I'm pretty sure that this agrees with the transformation of a strong connection, and then a strong connection immediately will induce a connection on the associated finite generated projective module. And somehow I have a feeling this is what we should check, but that it will be of that form. Except that, of course, this is here, everything's for universal calculus, but there's no problem to go to the quotient and verify that the formulas agree. So that was just a more of a comment than a question, but my question was about this formula, and you gave it to me, and it looks very, very natural. I somehow have a feeling that that the gauge transformation of a strong connection, when projected onto the associated projective module and this non-universal calculus, will agree with this formula.
Yeah, I wouldn't be surprised. I think in the general case, this stuff is very poorly understood, in the sense that there's not much of a unifying framework if you want to look at it from the perspective of arbitrary spectral triples and arbitrary Hopf-Galois extensions, for example. But if you want to talk about specific examples, I believe in von Seelekom's thesis, he computes a lot of stuff for the Hopf vibration over S4.
Yeah.
And in that case, I think he calculates the particular form of the strong connection and finds that it's more or less the same as the Grassmann connection, which is precisely the connection that produces these this stuff when you have a Dirac operator that you're working with. So probably for some specific examples, it's known, I guess. But I know also there's a lot of work that people like, for example, I think Cod is working on stuff.
Who?
Jens Cod.
Jens Cod, yes. You pronounce him in a very Danish way. That's why I didn't understand.
Who's well, is Richard still here, or is he?
No, he's gone. So now you can butcher the Danish as you please.
But yeah, he and also some other people try to tackle this from a very, very abstract KK theoretic way, trying to come up with some framework that combines all of these things in a sensible way. But I think it's straightforward to see, even in just the difference in approach, it's quite difficult in general terms to try and connect this stuff together. But yeah, for sure, there should be links.
Yeah,
Definitely.
and it's really not, when you mentioned Walter, I think it's really not so mysterious how you do it, at least in principle, because one of the many ways of viewing a strong connection is saying that this is a splitting of a multiplication map, which is left bilinear, right edge collinear, and this is this goes in the following way. This goes from P to A tensor P, where A is a subalgebra of P, so we have a well-defined multiplication map, and but this must be H collinear, where here you have the H coaction here and here, and left A linear. Remember, A is a subalgebra of P. So now, because of this collinearity, of course, we can just apply this cotensor product functor for this representation of a quantum group. And then of course you'll get immediately a map which goes from where? From P cotensor H V. Now this will go to A P cotensor H V. All right. But this is your projective module. This is your E. So you go from E into A tensor, and this is exactly the way Quillen wrote about connections. So having such a splitting of multiplication map on a projective module is the same as having, you know, the nabla for the universal connection. This is in papers of Quillen, Kunz Quillen. This is the standard stuff. So that you get from a strong connection, a connection of the associated module. That's just obvious. Everybody knows it. And there's no mystery really. And now, because we have a whole study with Ludwig actually of how you have gauge transformations acting strong connections, you can just see how it transforms from one picture to another. And I bet you'll get this formula. But it should be verified. Yeah. So that's really very straightforward, and I hope you guys do it soon. Okay, I think it's time to thank Adam again. That's been a very, very long discussion. So where's my hand to clap? Yes, here it is. Okay, so clapping hands. Thank you, Adam, very much. Very many nice comments in the chat. Thank you for a nice talk by people who had to leave. And before I stop recording, let me remind you one more time that in a week we continue with spectral triples, but this time it will be Alencon and Riemann zeta functions. So I stop recording. Thank you very much, and see you next week. Bye-bye.